Assalamualaikum and hello to everyone. In this video lesson, we will continue with the final subtopic for Chapter 3. In this video lesson, we will look at the remaining isentropic efficiency for steady flow devices at subtopic 3.9. As usual, on the right of the screen, written in red are the objectives for this subtopic. Okay, let's look at the isentropic efficiency for compressors. Now, we know that compressors are work input devices, meaning that the lesser amount of work input shows a better performing compressor. Unfortunately, for compressors, the actual work input is greater than the ideal work input. Therefore, in terms of isentropic efficiency, the isentropic efficiency for a compressor can be written as follows. The term for work input in the equation for ideal and actual condition is obtained by using the SFEE, steady flow energy equation. Next, let's look at the isentropic efficiency for nozzles. For nozzles, performance is based on the kinetic energy at the nozzle exit. The higher the kinetic energy at the nozzle exit, the better the performance of a nozzle. Unfortunately, for nozzles, the actual kinetic energy at the nozzle exit is less than the ideal kinetic energy at the nozzle exit. Therefore, in terms of isentropic efficiency, the isentropic efficiency for a nozzle can be written as follows, and the term for velocity, exit velocity at the nozzle exit is obtained using the SFEE, steady flow energy equation, and depending on the question, we can often neglect the inlet velocity at the nozzle exit because the velocity at the inlet is too low when compared to the velocity at the nozzle exit. Now let's look at the first example involving isentropic efficiency for compressors. You can pause to read and understand the question properly. Now from the question, one of the items asked to calculate is the work input for the compressor. This work input, since it involves isentropic efficiency, refers to the actual work input. For step 1, please try to draw and label the schematic diagram for the compressor. Now for step 2, to solve for volume flow rate, we will use the mass flow rate volume flow rate relationship equation. To find for actual work input, we will use the SFEE, and please remember to write down the conditions given in the question. Start with writing the general equation and cancel the terms based on the conditions. Write what is left and then rearrange to find for work input, and this is the general equation to find for the work input. We must rewrite the equation to take into consideration the ideal and actual conditions. Now for the third item, to determine the isentropic efficiency, we will use the isentropic efficiency equation for compressor. Remember to multiply it with 100% because we are required to find it in terms of percentage. For step 3, we find the required properties at each of the state. At state 1, remember to check for the phase of the substance before reading the properties. And using the appropriate tables, we will read for the properties specific volume V1, specific enthalpy H1, and also specific entropy S1. Specific entropy S1 is read because under ideal conditions, the specific entropy at state 1 is equal to the specific entropy at state 2. At state 2, from the given and known information, we can solve for the ideal conditions first. So using the appropriate tables, okay, we have to check for the phase, which we can see here. For ideal condition, the phase is superheated, and using the appropriate table, we will read for the enthalpy, ideal enthalpy at state 2, H2S, which we can see here is 296.81 kilojoules per kg. Next, we can solve for the actual condition. So using the appropriate properties, we will have to check again the phase. Okay, so for actual conditions, the phase is also in the superheated region, and using the appropriate table, we will read for the actual specific enthalpy H2A. For step 4, substitute and solve for the question. Okay, but before we solve for the question, we can sketch as required from the question the TS diagram for the compression process. Now for step 4, we substitute and solve for the question. For volume flow rate, we can see that the answer is 0.23368 meter cubes per second. For actual work input, we can see that the answer is 99.17 kilowatts. And finally, for isentropic efficiency, we can see that the answer is 81.4%. Okay, now let's look at the second example for compressors involving isentropic efficiency. You can pause the video to read and understand the question properly. Now, before we proceed with step 1, it must be highlighted since the question involves isentropic efficiency, 85%. All items asked by the question, okay, all items, the exit temperature here is the actual exit temperature, T2A, and the work input here is the actual work input, W in A. Now for step 2, since the substance is a gas, to find the actual exit temperature at state 2, T2A, we will use the SFEE equation, and remember to write the conditions given in the question. For the SFEE equation, we'll be using small letters, okay, lowercase letters, because from the question, the value for mass flow rate is not given. Start with writing the general equation and then cancel the terms based on the conditions. Rewrite what is left and then rearrange to find for work input. Remember that this is a gas, so H is replaced with CPT. And we can get the general equation to find for work input. This equation must be rewritten to take into consideration the ideal and actual conditions. And using both of these equations and relating it with the isentropic efficiency, we can solve for the actual exit temperature T2A. For step 3, we determine the required properties at each of the state. For state 1, just remember to convert the temperature in units Kelvin. For state 2, using the isentropic relationship equation, we can calculate the ideal exit temperature T2S. For step 4, to solve for exit temperature, from the isentropic equation, we can rearrange the equation and substitute the related equation. Then we substitute the values and we can solve for the actual exit temperature T2A, which we can see here equals to 1003.23 kelvins. And for actual work input to the compressor, we substitute the required values inside the actual equation and we can get the answer for actual work input, which we can see here 369.74 kilojoules per kg. Okay, the next example is involving nozzle based on the isentropic efficiency. You can pause the video to read and understand the question. Now, before we proceed with step 1, take note that the first item asks us to find the maximum exit velocity and the corresponding temperature. Both of these refers to the ideal condition for velocity V2S, for temperature T2S. For the second item, it asks us to find the actual exit temperature and the actual exit velocity. This is based on the actual conditions, V2A and also T2A. For step 1, please try to draw and label the schematic diagram for a nozzle. For step 2, to solve for maximum and also actual exit velocity, we will use the SFEE equation. Okay, please remember to write the conditions from the question. Okay, write the general equation and then cancel the terms based on the condition. Rewrite what is left and rearrange to find for kinetic energy at the nozzle exit. Okay, since the substance is a gas, H is replaced with CPT, and this is the general equation for kinetic energy at the nozzle exit. We must rewrite the equation for ideal and actual conditions. So for ideal equation, we can solve for the ideal velocity at the nozzle exit. For actual equation, we can solve for the temperature, actual temperature at the nozzle exit. To find for actual exit velocity V2A, we will use the isentropic relationship equation for a nozzle. For step 3, determine the required properties at each state. For state 1, since there are no properties, we can still write the given properties down. Remember that V1 here is neglected. For state 2, using the isentropic relationship equation, we can solve for the ideal temperature at state 2, T2S, which we can see here is 730.6 Kelvin. For step 4, substitute and solve using the required equation. For maximum exit velocity V2S, okay, we can see that the answer is 739.51 meter per second. For actual exit velocity using the isentropic efficiency equation, we can see that the answer is 681.79 meter per second. And finally, for the actual exit temperature T2A, we can see that the answer is 771.01 kelvins. Okay, we have come to the end of this video lesson. Okay, this also marks the end of chapter 3. Please refer to the original notes for exercises. If there are any questions, please do not hesitate to ask. Thank you for your attention and have a good day.